static equilibrium. Okay. So this chapter will be the basis for a whole course that you'll do. You'll do a course called statics, okay? And there's just two equations. And here are the two equations. Okay. The net force acting on an object needs to be zero, and the net torque acting on an object needs to be zero for it to be in equilibrium. So an entire course will be based on that, these two equations. You guys understand what I'm saying? So here's a bunch of forces acting on a system, and here are the torques of these systems, and they should add up to zero if you want the system to be at rest. Okay. And we'll come to that in a second. But here's the idea. Okay. So actually this chapter has two things in it. It seems like unrelated parts. Static equilibrium and elasticity. Okay. Now let me tell you where this will show up. Okay. So let's say you drive over this bridge. When you're driving over this bridge, what happens? You've added weight. Do you want the bridge to collapse? No. Yeah. The bridge, you want, well, essentially for it to not move, you want it to be in equilibrium. But what does happen? This cable stretches a little. After you drive away, what do you want for the cable to do? Go back to its original side. That's elastic behavior. Okay, that's where that comes in. How many times do you want to be able to drive over the bridge?
As many as you want.
Well, that's right. Okay, you want it to last as long as you want, as long as possible. Okay, so there's the elastic behavior. You want it to be in equilibrium, and you want your material, structural materials, to behave in an elastic manner. Okay. So that's the goal of this. So that's the kind of stuff you'll want to study in this chapter. Okay. All right. So we'll start off by defining the center of gravity. We've defined something called the center of mass before. Okay. Now, we've defined this before, and I'll come to that in a second. Now, center of mass and center of gravity will be the same point for small objects. For very large objects, center of gravity will be closer to the Earth than center of mass. Okay. What do I mean by very large objects? So, for instance, if you're trying to move Mount Everest, center of gravity for Mount Everest is slightly different than center of mass. Okay. All right, and then we'll come to conditions of equilibrium and all that kind of stuff. All right. All right, so there's the formula for the center of mass. So if here's an object, okay, you break this up into little pieces. Here's the mass of this piece, and there's the x-coordinate, y-coordinate, z-coordinate, okay. The center of mass would be calculated m1 times x1 plus m2 times x2 and so on, divided by the mass. Okay. Center of gravity would be m1 g1 x1, m1 g1 x1. G1 is the acceleration due to gravity at that location and so on, plus m2 g2 and so on. What the heck is going on here? G1, G2, what does that mean? G1 means acceleration due to gravity at this location. G2 means acceleration due to gravity at that location. Is G varying anywhere in this room? Is it?
G1?
No, is G, the acceleration due to gravity, varying in this room?
Yes.
Oh, it's pretty constant. Is it varying anywhere in this building? No. Is it varying anywhere in the tallest building in Daytona Beach? No. Will it vary in a structure that was 100 kilometers tall? Yes, slightly, very slightly. Okay. So for most objects that we consider, G doesn't vary. So all this would be constant, that would come out, and this would be the same as that. Okay. So it turns out that, okay, center of mass and center of gravity for small objects will be the same, but for very large objects, G at the bottom is higher than G at the top, so center of gravity would be below the center of mass. Okay. But most of the times, if you have to deal with the situation where the center of gravity and center of mass are different, you have arrived, my friend. Okay.
Is that because of the potential energy too for gravity, like mgh? Is
No,
it
it just depends on the size of the structure.
Okay.
Okay. All right. Now the reason we want to know this is because when you want to ask where does the weight of this object act, it acts at the center of gravity. Okay, and that's why we need to know that point. Okay. So when we calculate torques, you'll need to know where the force acts. Okay. All right. So for most cases, these two will be the same. The center of mass and the center of gravity will be the same for us. Okay. Only when the object is very, very large will it be different. Okay, so here's why we need to know. So for instance, here's a ladder leaning against the wall. Okay, we don't want the ladder to slip when you're climbing up the ladder. And so you need to know where all the forces are acting on it. And so the weight of the ladder acts at its center of gravity, and that's why we needed to know that. Okay? All right, so we'll come to that. Now, before we go further, let me do the following. Let me motivate this chapter. Okay. So here's an object. I'm going to apply a 10 Newton force and a 10 Newton force like that. Will this object move? No, it won't move. So, okay, so here's now it's not a point object, this is a ruler. Will this object move? It won't move. How about now?
Yeah.
So what will happen?
Like you know the central.
Yeah, it'll spin about its center of mass. Okay? So here's the point. If you have a point object, the only condition you need for equilibrium is the sum of the forces be 0. Now, when you come to an extended object, that condition is satisfied, but that's not enough to ensure that it remains at rest. It remains in equilibrium. What you find is you need an additional condition that the sum of the torques be 0. The sum of the torques was 0 in this case, the sum of the torques was not 0 in this case. And so you have non-zero angular acceleration in this case. Okay? So whenever you have extended objects, you need two conditions for equilibrium. The sum of the forces acting on the object should be 0, and the sum of the torques of these forces should be 0. The sum of the torques for the forces are 0 in this case, they're not 0 in this case. Okay? So for extended objects, you need these two conditions. And this is an entire course, these two equations. Okay? You guys understand? All right, so even if you have an extended object, and here's the center of mass, and all the forces acting on this guy go through the center of mass, then this is the only condition you need, because all the torques about the center of mass are zero. Okay? So then in this case, you can treat this as a point particle, as long as all the forces are acting through the center of mass. Okay? But in general, all the forces won't act through the center of mass. So for instance, so here's a problem, here's the ladder, here's the object, here's our extended object, and the forces on this guy are, there's one force that is being exerted by this wall, there's the normal force exerted by the floor, there's the friction force exerted by the floor, and there's the weight of gravity exerted by the earth on it. So here are a bunch of forces acting on this ladder, okay? And if you want this ladder to be at rest, what should be true now? So we need two conditions. The sum of the forces should add up to zero, okay? And the sum of the torques of these forces should add up to zero. Okay? And then it'll remain at rest. Okay? All right. All right, so for small homogeneous symmetric object, the center of gravity as well as its center of mass are the same, okay? Which is its geometric center. All right, now before we get into those details, but this is the punchline of this chapter. Okay? I know there's some confused looks I see, so I'll pause and let you guys ask questions. All right, we'll come back to that in a second. What I want to make sure is, do you understand this fact? This should be easy to understand. Okay? The torque of this guy is going to make him rotate clockwise about that center of mass. This guy is going to make him rotate counterclockwise. So this will be a negative torque, this will be a positive torque of equal magnitude, and they add up to zero. Okay? In this case, that's counterclockwise rotation, positive torque, counterclockwise rotation, positive torque. So the torques don't add up to zero. Okay? Okay. So as long as we understand this is good. Okay. We'll understand the rest of that in good time. Okay. All right, so here's a pretty picture. Well, that's a matter of taste, but anyway. Why is this pretty? What's special about this picture? You notice anything?
The objects,
What?
the forces, obviously zero, and the torque is zero, because the objects are stacked further out of
Right.
the station. It's not moving.
All right, so watch this. Will this stay on the table? No. But look at this. This guy is entirely past the edge of the table. And he's balanced. That's what's neat about it. Okay? You don't need any cement. So you could build an overhanging awning, okay, like this. Okay, how is this happening? Okay, so for this guy to be balanced, okay, what needs to be true is his center of mass, once his center of mass goes over the edge, then he'll topple over. As long as his center of mass is behind the edge, he'll be fine. Okay. So the center of mass of this guy, is behind that edge. The center of mass of these two guys is there, behind that edge. The center of mass of these three guys is behind that edge. And so on. Okay? So there's an awning that you can build, and you don't have to nail that thing down. Okay? Looks pretty, and it gives you shade as well.
Hold things above it.
What's that?
Can it support another structure above it?
Yeah, well, you can put another plate. You can go home and make this with Jenga things. Okay. And all right, sharp edges are good, so you don't want smoothed out Jenga blocks. But anyway, yeah, you can keep going. Here's another neat wine bottle holder. Okay, what's going on here? All right, what's that?
Oh, well, gravity's pushing the end of the bottle down on the right, so that's bringing up the cap on the left. And since the board is leaning forward, it's kind of equaling out at the center.
Right.
Vertex, let's see, like the vertex between the two.
All right, so okay. So here's another way to look at it. So I'm going to draw a person. All right, that's no, okay. Well, I was going to draw it because I'm recording this. But anyway, the idea is the following. So when you're standing up, okay, for you not to fall down, what needs to happen is your center of gravity needs to be within your footprint. If you want to fall down, all you have to do is bring your center of gravity outside your footprint. Okay? For this object, there is the footprint. Okay? So, this thing, the center of gravity of this object is right above this footprint. So this wouldn't work for an empty bottle. So this thing is designed for a full bottle. Okay? So anyway, as long as the center of gravity of this object is above the footprint, it'll be balanced. Okay? Okay, so if the center of mass of the object moves with the, yeah, okay. By the way, so we want to define these terms. So static equilibrium. The term equilibrium refers to, okay, so this is where it comes from. Equilibrium is when the net force acting on the system is zero. That means the acceleration is zero. So equilibrium refers to the fact that acceleration is zero. And since we're dealing with extended objects, we want linear acceleration to be zero and angular acceleration to be zero. All right. So when acceleration is zero, is the object at rest? Not necessarily, okay? If the velocity is zero as well, then it's called static equilibrium, okay? And if velocity is constant and acceleration is still zero, this is called dynamic equilibrium, okay? So, for our bridge, do you want your bridge to be moving at constant velocity? No. For a lot of our structures, we want static equilibrium, okay? You want the acceleration to be zero and the velocity to be zero as well, okay? So those are the two terms you need to be familiar with. All right. So for a point particle, the only condition for equilibrium is the net force be zero. Okay, so going back to our diagram here, there is the point particle. For this point particle, if you have several forces acting on it, for it to be in equilibrium, all you need is for the forces to add up to zero. But soon as you start dealing with an extended object, here the sum of forces is zero. Here the sum of forces is zero. But this object is not in equilibrium. It's got alpha, which is not non-zero. It's got angular acceleration. Okay, so when you deal with extended objects, not only do you need this, you need that the sum of the torques be zero. Okay, so in this case, there was positive torque, and this was not satisfied. Okay. So for extended objects, you need that the sum of the torques be zero as well. An additional condition for equilibrium is needed, which is that the net torque evaluated about any point be zero. Okay. By the way, here's an interesting device. I'm sure you guys have seen this thing. And again, with all these pictures, these pictures are meant to be misleading. Again, again, since this is balanced, okay, just like your footprint, the center of mass of this guy is right below the point of suspension. So the center of mass of this guy is somewhere there. So are all these penguins of equal mass? Looks like it, doesn't it? All right, so let's say if this distance, okay, this is 1 inch, 2, 3, 1, 2, 3. So let's say this distance is 3 times this distance. Then it turns out that if this mass is m, this is 3m. Okay, x, 3x. Okay. Again, so this is x, 3x. So now this guy is 4m. So this guy is 4 times 3, 12m. X, 3x. Okay, so this is 36. Okay, so that's what's going on there.
So that first pavement, right, number
Mhm.
one, would technically be heavier in order for all these not to fall down.
That's right. I mean, you've done seesaws, haven't you?
Yeah.
So there you go. Okay. So very deceptive there. Okay. You guys understand 3m times x. This torque was balancing m times 3x. This torque was balancing this torque. Okay. So there is the mass times gravity will cancel. There's the moment arm. Okay. There is the force. There is the moment arm. Okay, so you will see you'll see sculptures like these, and so they're counterbalancing weights. Okay. Anyway, we will be interested in static equilibrium of extended objects, and so you need these two conditions. The sum of all the forces acting on the object should be zero, and the torques of all those forces should be zero. Okay. All right. Now, so in most cases, what we'll do is, okay, when you come to your statics course, then you will be dealing with three-dimensional forces. But right now, you'll get your, we'll start off by dealing with two-dimensional forces, and then the torques of these forces will be in the z direction. So you will be dealing with three forces. The x component of the forces should add up to 0, y component should add up to 0, and the torques, which will be z components, should add up to 0. So you'll be dealing with three equations, okay, and then you can solve problems with three unknowns. All right, so that was all a bunch of, equations. So let's apply it to a real world problem. Okay. So here's a construction site device. Here's a scaffolding. Okay. Now, if you're designing this scaffolding, you want to make sure that this cable is strong enough so that how many ever people are there that you will encounter, and no matter where they're standing, you don't want the cable to snap. You don't want the hinge to snap. You don't want this thing the scaffolding to fall down. Right? All right, so under all kinds of conditions, what is it that you want? You want this to be in static equilibrium. So you want this to be in static equilibrium, so all the forces that this guy faces should always add up to 0, and all the torques of these forces should add up to 0. Okay? So let's look at the forces that guy. So the forces this guy encounters, this plank encounters. There's the tension in the cable. There's the weight of the plank itself, gravity pulling him. There's the weight of the person, so the person is being pulled down by earth, and then he pushes down on the plank. So there's that force. And what is this force? So this diagram is showing you all the forces on the plank. What is this force? That is the hinge pushing on him. Okay? So this cable is pushing this guy against the wall, and that's the wall pushing back, if you want. Okay? So now what you have done is you've isolated the object of interest and shown all the forces acting on this object. And you don't care about the rest of the stuff. This is called a free body diagram. Okay? So you're looking at only the object that is of concern to you. Okay? What is it that you want of this object? You want it to be in static equilibrium. You don't want him to move. So what should be true? The sum of these forces should be 0, and the sum of the torques of these forces should be 0. Okay? And that's the problem you want to analyze. Okay? You guys understand? So we've boiled it down to the essentials. Okay? All right. Now, so that's the free body diagram. So let's look at some of the points here. Okay, isolate the object being analyzed. Draw free body diagrams. So this is the free body diagram we drew. Show and label all external forces. So we've shown all the external forces acting on the object. Those are all the external forces. Indicate location of all forces. You have to draw the location precisely. You can't draw the tension here. That would be wrong. Okay? So you have to show the precise location at which the forces are acting. You can't draw the weight of this object there. The center of gravity is there, and so that the weight acts there. Okay? Indicate locations of all forces. For systems with multiple objects, draw a separate free body diagram for each object. So you might have a multiple object system. You're analyzing each object separately. Okay? All right, so there's the free body diagram. What have we done in going from here to there? What have we done? We've replaced this force by its components. This force is the same as the sum of these two forces. Okay? We've replaced this force by these two forces, the x and y components. And the reason is because it's easier to deal with. It's more convenient to deal with the components. Okay? So the behavior of this guy and the behavior of this guy are identical. Okay? All right, so there's our free body diagram. You guys with me? You guys looked a little tired. You need a little break? Are we good? You want me to stop the lecture? All right. All right, so there's the object. All right, so what is it what is it that we want? We want this guy to be at rest. So what we said was we want the sum of the forces to be 0 and the sum of the torques of these forces to be 0. Okay. Now when you calculate the torque, okay, so when you calculate the torque of this force, well, you calculate the torque about some point. Well, which point do I calculate the torque about? So here's the theorem. If the torque of a bunch of forces is 0 about some point, it's 0 about every point. So it won't matter what point you calculate the torque about. Okay? So if it's 0, the sum of a bunch of force, the torques of a bunch of forces is 0, then it'll be 0 about any point. So it won't matter about which point you calculate. So you use that to your advantage. So if you don't care about this force, then you calculate all the torques about that point. Okay? And then you're eliminating one of the forces. That's the idea. Okay? All right, so choose a convenient axis for calculating net torques on the object. When the net torque is 0, the choice of axis is arbitrary. Okay? A force that acts along a line passing through the axis produces 0 torque. So if you calculated the torque about this guy, the torque of this guy will be 0. Okay? And so if you don't know that force, that's where you want to choose to calculate the torques. Okay? All right, when we get to problems, you'll understand this better. Okay? All right, so let's say you go bowling, and now from a physics perspective, this is the essential drawing. Okay? So you're ready to roll, and right now you want this bone to be at rest. Okay? Well, let's look at the forces on this bone. Okay. What is this guy? That's the weight of the bowling ball. Gravity is pulling it down, and that's pushing you down. That's pushing the arm down. Okay, so you're looking at this whole thing. So that's pushing it down. What's this force? Hmm?
Is that the tension?
The tension in the muscle. Very good, my friend. That's the tension in the muscle. What is this force? That should be right there, so the diagram is done. That's, okay, this tension is pulling this bone against that, and that bone is pushing you down. So that's that force. All right, so let's say we're not interested in this force. We'll calculate the torque of all these forces about that point. So here is how much are bowling balls? 15 pound, roughly. So here's a 15-pound bowling ball. Let's say that's about an inch, and that's about 10 inches. Okay. So we'll call this X and this 10X. So I'm going to point out an interesting thing. So here is a clockwise torque, and this will provide a counterclockwise torque about this point. So F times X minus mg times 10x equal to 0. All right, so I don't know if that's sunk in yet, but the tension in this muscle is 10 times the weight you're lifting. I'm being kind here. It's probably a lot larger than that. This is probably about 15x. Sounds like a pretty bad design to me. What's going on here?
arm is causing the bowling ball to have, causing more tension in the muscle.
Right. Yeah, so if you are a designer, to lift a 15-pound object, you to design a structure that's bearing a 150-pound load, you're not a good civil engineer, my friend.
I wouldn't be so sure. I'm sure there's a purpose.
Yeah, so that's the question.
That's why they say look at your knees.
What's that?
And that's why they say look at your knees.
Right. So what's going on is the following. If you apply a larger force, you move smaller distance for a larger motion here. And if you want to lift your arm up, let's say you lift this ball up 10 inches, your arm moves here. At this point, it only moves about 1 inch. Okay. And it's harder to contract and stretch muscles. That's why you're willing to put in more load. A smaller motion is magnified as a larger motion there. Okay. All right. So leaning ladder problem is a standard problem. Here is the ladder. We don't have you climbing up here yet, but you don't want this ladder to slip when you climb up. Okay. So right now with this ladder leaning, this wall exerts a force like that. We are assuming a smooth wall, so there's no friction. It's exerting a normal force. There's the ground exerting a normal force. There's the static friction preventing the ladder from slipping. Okay? And you want this to be as large as possible. That's why they put the rubber boot at the bottom of the ladder. Okay? And there's the weight of the ladder. Okay? And again, if you don't want this moving, the conditions you want are the sum of these forces should be 0, and the sum of the torques of these forces should be 0. Okay, so let's say you're calculating the torque about this point. This force is going to turn the ladder counterclockwise, which is a positive torque. This is going to turn it clockwise about that point, which is a negative torque. These two will have 0 torques. Okay, so this torque is being balanced by this torque. Okay. All right.
What is P representing?
That's,
Force from the wall?
yeah.
Okay.
Yeah. Okay. All right, so actually we'll stop here, okay, because